Hello and welcome to the Plus podcast. I'm Rachel Thomas.
And I'm Marianne Freiberger. How do you feel about traffic cameras, Rachel?
Well, I don't know, Marianne. I didn't feel that enthusiastic about them last year when they justifiably caught me speeding in my car. But, to be fair, they did correctly capture that information, and I'm happy to report I have learnt my lesson.
Well, I'm glad to hear that. But it turns out that catching you speeding isn't the only thing traffic cameras can do. They could also change our understanding of how we move around our cities. And with this understanding, local governments could make changes to reduce the number of accidents and encourage walking and cycling, all of which would have a great impact on our health and on our environment.
Now, once upon a time, in order to get that sort of information, it would have taken some unfortunate person sitting down and analysing hundreds and thousands of hours of traffic footage. But in this podcast, we'll hear about new advances that allow computers to automatically understand what a traffic camera sees, identifying whether people are in cars or trucks or tuk-tuks or bikes or if they're walking. And doing that needs a lot of maths.
So in this podcast, we'll be talking to a number of researchers involved in the Integral project about how they are using remote sensing data from India to understand traffic. And amazingly, they are using the same maths and the same technology away from city centres to understand the health of forests.
The Integral project is made up of researchers at the University of Cambridge and researchers and industry partners in India. The name is based on the phrase India Remote Imagery Analysis. It's a really fascinating collaboration between people who collect the remote sensing data, such as the video from traffic cameras and satellite images of forests in India, and researchers developing the technology to analyse those remotely gathered images to answer meaningful questions. Carola Bibian-Schernlieb is Professor of Applied Mathematics at the University of Cambridge and a good friend of Plus. She is co-leader of the Integral project, and so we asked Carola about the motivation for the work.
So I guess the motivation was a mixture between mathematics and the application. So maybe I'll start with the latter. So remote sensing really is a major mean for mapping our world at scale. This includes, imaging data coming from satellites, from airplanes, but also closer to the ground from traffic cameras, for instance. Now, this data, of course, by itself is useless if we do not have the means to analyze it, to extract really the information from it that we are interested in.
To extract the information Carola and her colleagues are interested in, they need to use the mathematics of image analysis. But in order to do this automatically and in real time, they also need to use machine learning. Now, machine learning is the most significant recent development in artificial intelligence. And it involves a machine learning by itself, learning how to do complex tasks directly from experience, from data, of doing that task. In practice, this is done using something called a neural network. For example, if the task is to look at images and identify types of road vehicles, the computer feeds these images into the neural network, and the aim is for the network to output the labels of the vehicles that it has identified in the image. So whether it's a car, a lorry, a tuk-tuk, or a bike.
You can think of a neural network as a big mathematical equation built from layers of smaller equations, and these layers are linked together according to some parameters governing how one equation feeds into the next one. I like to think of the parameters as kind of the knobs of the neural network, and a machine learning algorithm gives instructions for turning the knobs in order to tune the network to give answers that match the training data. The computer learns how to do this by looking at lots and lots of training images, which have already been annotated with the correct labels. This annotation is usually done by hand by researchers. Then for each training image, the computer checks its own outputted labels against the correct labels and tunes the parameters of the neural network according to some rules given by that machine learning algorithm. If you give a neural network enough training data annotated with the labels you want the computer to give, the parameters can be tuned to give incredibly accurate results. So the idea is once you've trained your neural network, it can automatically extract the information you're looking for from real-life images with incredible accuracy. Here's Carola again.
So AI really promises to extract such information from this data at scale. However, state-of-the-art AI approaches such as deep neural networks do this with a price in mind, which is that they need lots of very high quality annotated data to be trained with. And in applications where we are dealing with real data, in countries, such as India, but I would say in general, such annotated data is very costly to obtain, is very time consuming to obtain, either because expert knowledge is required to do these annotations, and or because there is a lot of manual work involved in order to collect the data on the ground or sit in front of a computer and do these annotations. So and this is exactly where the mathematics comes in, and where now the mathematical motivation as well comes in of Integral for tackling these issues. So with where the idea of Integral was to introduce more structure, more mathematical structure into these AI approaches in order to develop methods that can handle the small annotated data regime.
The Integral project is looking at two different sources of remote data from India: satellite images of forests and traffic camera videos from cities. We asked James Woodcock from the Centre for Diet and Activity Research at the University of Cambridge about how his research fits in with the project.
So I'm very interested in studying how health can be improved in transition to zero carbon transport, and walking and cycling are really important modes for health and low carbon, but they're often not measured well. And we want to know about how many trips were made, where they're made, who makes them, and about traffic safety with danger from motor vehicles. And different kinds of image data and computer vision can help paint different parts of the picture for understanding this. And traffic data can tell us a lot about how many trips are made, who is making them, and can give us very detailed information on interactions with other road users. They can also be used to look at short-term and longer-term changes over time.
Angelica Aviles Rivero, a mathematician from the University of Cambridge, is working with James on this traffic research to develop efficient and generalizable machine learning tools to analyze this data.
The main goal of the traffic team is to develop innovative, efficient, robust, and generalizable tools for the analysis of urban level video data for India. So the main goal here is to provide an easier way to analyze vast amount of data in an incredible short period of time. And why this analysis is relevant is because we can provide this knowledge to help modelers and policymakers, for instance, like James, for supporting their decisions.
I mean, these data, are useful all over the world. People are working with this in the UK, in the US. But I think these data have the greatest value in places where we have less traditional survey data. If something is not measured well and it's not measured over time, then designing and monitoring effective policies is very, very difficult. And if we can get these methods out there and they can be used at scale, then it's possible to kind of leapfrog a lot of what has been done in the West. And, this is so important in terms of the, climate change, achieving sustainability, and, as has been said already, the very high burden of traffic injuries, of air pollution, of noise pollution as well, which has major harms on population health, that we see in many Indian cities.
A really exciting and innovative part of the project is the collaboration between India and the UK and between experts working on the ground capturing the remote sensing data, researchers working on the technology of extracting the information, and researchers and policy specialists looking at the potential impact of the work. Saurabh Pandey is from Critical Solutions in India. They are one of the industry partners, and they provide the traffic camera data for the project. Saurabh told us that the impact of traffic on health is an obvious motivation for their work on the project.
As per a recent report which was published, there are around 3 out of 10 most polluted cities. There are around 3 cities are in India, including Delhi. So, and also probably the fatality rate by road accident, that is also one of the highest in India.
The hope is that analysis of traffic data from around the world might help inform public policy and improve people's health. Saurabh and his colleagues capture and review video from traffic cameras and mobile cameras by the road in India, and they identify and label vehicles such as trucks and tuk-tuks in stills in these videos. Then the plan is that these labeled images are used to train a neural network to automatically extract the number and types of vehicles using the roads in live traffic camera video.
And this is not a straightforward problem. As you mentioned, this requires effort from all different disciplines, including capturing real life data from ground using traffic camera as well as the mobile platforms. Then annotating them to maybe to help the mathematical tools. And possibly, extract some information out of it so that it can help.
Sanjay Bisht is from Iora Ecological Solutions, another one of the partner organisations based in India. Sanjay and his team are contributing to the forest research aspect of the project. The aim here is to automatically identify species of trees using images taken from the air. Iora Ecological Solution provide the labelled satellite images of forests, but also take the algorithms Integral develops and validate them in the forested regions of India.
So the basic idea with the whole project has been to identify the type of species in a particular land patch we are analyzing, right? So just think of it as taking a photograph from an airplane, and then I'm asking you, okay, you see these many trees, tell me what the species are. Okay, so now obviously a normal human can't do it, but with the advancement in sensors and the AIs that we are working on currently with the Cambridge University, it's fairly possible to do it. So it's not that accurate in the moment that we would like it to be, but it's still accurate.
Sanjay explained that it's really important to have local knowledge, initially just to collect the data and navigate all the local administrative red tape, but you also need the human interaction, the people who are on the ground like Sanjay, to accurately annotate the data to train the AI.
To train that AI, that artificial intelligence, that the data to intelligence part is where you have to have some human interaction. Now, this is where we come in. We tell that, okay, the one that you see as, red patch is not actually mango, it's something else entirely. So the sensors would tell you, okay, this is the color of a particular pattern, and the data that we collect will tell you that this pattern belongs to this species. And this is how we train the data set. So the data, the basic data that tells you, okay, what the whole scenario you are seeing here is actually this and not this. is what we do.
So you can see why you need local people with this local knowledge and local connections to make this whole thing work.
Yes, and this kind of work is so important as it gives sort of this new technology to monitor the biodiversity of forests, which is so important environmentally. If we don't monitor it, we don't know how to keep it safe.
So the team in India, including Saurabh and Sanjay, are providing this remotely captured data. And we've already heard that a neural network normally needs huge training sets of label data. But producing these, whether it's for traffic or trees, is too expensive and time-consuming. So how can we make do with smaller sets of label data? That's what the mathematicians in the Integral team are working on. We asked Debmita Bandyopadhyay from the University of Cambridge. She is developing and testing algorithms to map species of trees in the forest data as part of her postdoctoral research.
The importance of this algorithm development for this particular, whatever remote sensing data is collected, is that whenever the ground data is collected, we do not have a lot of area covered in that particular remotely sensed area. So there are a very large amount of spaces which do not have labels. Now, when those don't have labels, we need to train based on the sparse information that we have on ground. So that's where the complicated deep learning, the machine learning algorithms play a huge part, where from the small amount of information that is captured on ground, it can accurately predict the other area which does not have labels. This particular robust algorithm development is very important, so that it's always not a mandate to go physically and validate our results.
Debmita told us about the exciting new approach the Integral team are developing to handle this situation of training a machine on a small or sparse training dataset. Traditional machine learning, as we heard before, relies on a vast set of training data, annotated with the labels. But the Integral team are working on what they call semi-supervised learning techniques, where you first extract as much structure as you can from both the labelled and unlabelled data that you've gathered. So in the case of the Integral project, they're representing the data they have gathered as a graph, a network of points representing the individual images collected, and where 2 points, 2 images of traffic or a forest, are linked together in this graph if they share some sort of features. And then this graph structure is used to propagate the labels across the whole data set.
Yes, and it's amazing how they do that. So they imagine the labels diffusing through the graph using the same kind of mathematics that is used to model heat diffusion through materials. Debmita told us about the new techniques the Integral team has been developing to do this.
The techniques that we are developing are the most recent ones which have been done on standard data sets. So we are doing it now on real-time data sets, which is a huge challenge, where a lot of mismatch or misinterpretation can take place, because the forests in India are mixed forests. From one pixel to another, the species can change. So that's where we are using this particular algorithm called the graph learning method. So it's a very new technique that we are applying, and especially on a real-time data. So I think it's a very new thing that we are doing here, and we are facing challenges, but yeah, we are reaching there.
We asked Rian K, a mathematician from the University of Cambridge, about how he's using this semi-supervised learning approach to identify vehicles in traffic camera data.
Semi-supervised learning is in contrast to other machine learning methods like supervised learning, which trains deep neural networks to predict by feeding them with a lot of training images. All these images have to be labeled by human. However, this is not realistic in the practical problem that we have, because of the large amounts of images we have, and the fact that labeling these images is very time-consuming and expensive. What we do to mitigate this issue is through semi-supervised learning, where we manually label only a small number of images and then combine them with a large amounts of unlabeled images. The mathematical modeling in our techniques then used to make deep neural networks predict consistently and confidently on the parts of images that we do not have any labels. So in summary, with our semi-supervised learning methods, we're able to provide a more robust and efficient solutions for analyzing the data we have with better performance, but requiring less manual resources.
Carola Bibian Schönlieb again.
So on a mathematical level, we have heard, from all of us, I think, who have spoken so far, that the challenge comes from wanting to apply these wonderful AI techniques, but not having enough annotated data to train them efficiently. So now this definitely is an overarching theme that happens both in the forest project as well as in the traffic arm of the project. In our particular case, we have been developing these graph-based learning techniques, these graph-based clustering classification techniques. This is a very, very promising direction to go for these type of approaches. The other one that will come up more in the traffic project is another kind of strategy to put more structure into the AI approach to be able to mitigate the fact that you don't have so many annotations, is the idea of multitasking. So profiting from the fact that if you want to do, for instance, species classification on hyperspectral imaging data, that knowing and delineating at the same time individual trees might actually help also the species classification. Because it adds more structure to the species classification problem, and the other way around. If you do species classification at the same time as you do individual delineation of trees, you can profit from combining these tasks into one.
So surprisingly, sometimes doing two things at once can actually improve your performance. Delineating individual trees, so identifying which parts of the image are one tree and which parts of the image are the next tree, can actually make it easier to then classify which species each tree is, and vice versa. Angelica Aviles Rivero explained how this multitasking approach fits in with the work of the traffic team, where the tasks such as identifying which parts of the image contain a vehicle is done simultaneously with the task of identifying what kind of vehicle it is.
Behind these algorithmic techniques, as I mentioned, is a very challenging task. So the team is doing these great efforts, how we can increase the performance with this challenging task. So we, as Carola and Juan mentioned, we have different paradigms, including in the solutions, not just semi-supervised learning, but as well, another keyword is multitasking, how we can increase the performance by merging simultaneously different tasks. But this is the so-called holistic approach. Holistic means how different principles in algorithmic techniques and fusioning in a single solution.
So Carola has told us about the mathematical links between the traffic and the forest part of the project. But there's also an important link between the two parts of the project in terms of applying these new mathematical techniques. David Coombs is from the Department of Plant Sciences and the Conservation Research Institute at the University of Cambridge, and he's a co-lead in the Integral project. We asked David about how the applications of these new technologies link together the two sides of the project.
So we have a whole suite of new technologies coming on board. There's many more satellites in space sensing many more things now. And we've got these AI approaches coming on board as well. And they can be used to tackle a whole raft of interconnected environmental questions. So what goes on in cities, these urban spaces, is important for people, but also what happens in forests around those cities is important for people as well. And so there's strong linkages between the different components of Integral because of these pressing and complex environmental issues which are happening around the world as human population increases, demand for resources increase. It's putting pressure on nature and those new systems, those new ecosystems in cities are affecting people's health. So we need a connected approach for this to work, and that's what Integral is providing.
That's all we've got time for in this podcast. Thank you very much to all the Integral team in the UK and India for taking the time to talk to us over Zoom. You can find out more about their work and about image analysis and machine learning on plus.maths.org. Thanks for listening to this Plus podcast. I'm Rachel Thomas.
And I'm Marianne Freiberger. Bye bye for now.